Hey, welcome back. This video, I'm going to make two sections of this video. This one's the first one, and this one talks about the sum and the difference formulas. The second one is also going to be on sum and difference formulas, but that's the one where we're going to be proving, um, proving left-hand side equals right-hand side using these sum and difference formulas. But this one is not about proving. This one's more about finding the exact values. So hence the other one kind of builds upon this one. Let's go ahead and start it with the basic of sum and difference formulas. Well, first of all, here we are. Here are the sum formulas and here are the difference formulas. If you notice, we have cosine, sine, and tangent sum formulas. Why are they called sum formulas? Because all of them have addition down here. And on the other side, we have the difference formulas. Why? Because all three are subtraction, subtraction, subtraction. A and B, A and B, A and B. A and B, of course, refer to some combination of angles. So this could be called as sum of two different angles, and this could be referred to as difference of two different angles. I do want you to know that some books, and sometimes even in our questions, instead of seeing A and B, you might see alpha and betas. Same thing. It's just looks fancy, looks different. So that same formula could be written as cosine alpha plus beta is equal to cosine alpha times cosine beta minus sine alpha times sine of beta, where what is alpha beta? Alpha beta angles. What's AB in the above formulas? Also angles. Just want you to know to be familiar with that. Then comes in the fact that now that you know the formulas, also know what is not right. So for example, if I have cosine of some sort of angle here and some sort of angle here, that does not equal cosine of angle A plus cosine of angle B. That does not equal that. In fact, it equals the formula that's been given to us. Very, very different. If I were to write it as an angle, let's say we have cosine of 45 degrees plus 30 degrees, that is not going to equal cosine of 45 degrees plus cosine of 30 degrees. That's not going to be the case. If we use angles that are special right triangles, we can actually, we may or may not be able to prove it. Like this is basically cosine of 75 degrees, and this is cosine of 45. We do know the value is root 2 over 2. And cosine of 30 is root 3 over 2, and that's about root 3 plus root 2 over 2. That's that value. If I plug this in the calculator, obviously I'll be able to get the decimal value for it. If you plug this in the calculator and get decimal value for it, those two will not be the same because that's not how it works. These are the formulas that actually make it work. All right. Erase that and let's get started. There we go. Okay. So our first example. This one says find exact value. Well, first of all, we have talked about exact values and what that means. Exact value means don't be using decimals, don't be rounding your answers. Whatever it is whatever it is. Which means if I end up with root 15 over 4, leave the answer like that because that's the exact value. And we've talked about this in first semester also. So find the exact value of cosine of 75 degrees. And yes, this is no calculator. All of this is no calculator, which means they're saying, hey, find me what's the value of cosine of 75. Well, the closest I know, we do know cosine of 45, which is root 2 over 2. Then the next thing we might know is cosine of 60, which is half. And then the next thing we know is cosine of 90, which is 0. Now cosine 75 is somewhere here, so the best approximation I can get is it's somewhere between 0 and half, right? But not, I don't know the exact value like that. That's when these formulas, sum and difference formulas, come in handy. The first thing you want to do is you want to break this 40-75, and I'm starting off with degree kind of questions because our mind works better with just numbers. The idea is to break it down into two numbers where both of them are going to be special right triangles. Because we know our special right triangles. If we can break it down into special right triangles, we can evaluate those values and get to the answer. Obviously, there are gazillions of combinations where 75 can be written as 10 and 65, but obviously you're not going to pick that. 25 and 50. We don't know our 25s and 50s either. So if you look at this, it's best to split it up into 45 plus 30, because we know our 45s from the unit circle, we know our 30s from the unit circle. And hence, this would be the best combination. This would be the best way to break down 75, which probably will come to your mind right away. I mean, you wouldn't be thinking of 10s and 20s like I did. I just wanted to show you the concept here. So I'm like, okay, I am going to take this 75. I'm going to break it up into cosine of 45 degrees plus 30 degrees. It's still cosine of 75 degrees. Now, when I do that, I can clearly use the sum formula for cosine. But what's my a value? Clearly, this is the a value and this is the b value, which means if I expand this using that top formula, that formula says this must equal cosine of A times cosine of B minus sine of A, which is again 45 degrees, and times sine of B, which is 30 degrees. And now all these are values we can evaluate. Again, get to practice your unit circle, because again, basically for all these four, you don't want to be drawing triangles. And if you want to, it'll just take up more time and there are more chances of error. By the way, just to clarify here, this is the A, then B, and then A, then B. You got to make your A and B consistent. And clearly the formula just works out. Just going to rewrite it. Cosine of A times cosine of B minus sine of A times sine of B. And now we're going to start plugging in those numbers or values. Cosine 45 is root 2 over 2 times cosine 30 is root 3 over 2 minus sine 45 is root 2 over 2, and sine of 30 is half. And once I have the values plugged in, from here it turns into a computation problem. It just depends on how good you are with numbers. PEMDAS is all what needs to be followed here. Root 2 times root 3 is root 6, 2 times 2 is 4, minus root 2 times 1 is root 2, and then 2 times 2 is 4. And then the best I can do with this is combine the denominators because they happen to be the same. So I can combine them. And cosine of 75 degrees is equal to this. We can shortly verify. You can plug this into the calculator. You can plug this into the calculator. They both should have the same decimal value. And in the beginning, I recommend do it just to make sure you've done your work correctly. And I have the exact value. Like I cannot combine this anymore. There's no radical in the denominator, so there's nothing to be rationalized. It is what it is, and this is the exact value. Why it's the exact value? Because root 6 is going to be a long decimal number, root 2 is going to be a long decimal number. I won't be able to get anywhere without rounding, and that kills the purpose of the exact value. I'll show you another example that's also in degrees. It's a longer problem, but is in degrees, so you can have a feel of longer problems. This one says find exact value of tangent of 195 degrees without calculator, obviously. Just from the unit circle, I do know that this part, which is 180 degrees, that's the closest I could get to 195, is a negative 1 comma 0. So the tangent value there is a y over x, which is 0. So tangent of 180 is 0. So my answer is going to be close to 0. It's not going to be 0 for sure, because 195 is somewhere here. Just to put things in perspective. So the same idea, tangent, addition, and subtraction formulas are also listed and you have access to them. The idea is to break down 195 into two numbers that are special right triangles. Generally start with 30 just because that's the first one we know. Once I subtract 30 from it, I get 165. So obviously that's not going to work. 30 works, but 165 doesn't. Move on to the next special triangle. So 60 and 135. So 60 we can handle. 135 is also on unit circle. 135 is the actual angle. 135 is this angle right here. So the reference angle automatically is a 45-degree angle, and hence we can figure out the values of all of this. So this combination works. It was the second one I tried and it works. Like, are there more possible ones? If I subtract 90 from it, I get 105. So this I can handle, but this I can't. And the next one will be 180. But then that's 15. So we can handle this, but we can't handle that. So this is the best combination. I'm going to break it into 60 and 135. 60 and 135. It doesn't matter which one you write first. Oops, 60. All right, and that turns into tangent addition formula, which tells me, I'm just going to follow this formula now. In the numerator, it says we have tangent A plus tangent B plus tangent of 60 degrees over 1 minus tangent of A again, but times tangent of 60 degrees. And clearly there is no operation between the two. It's automatically multiplication. Then comes in putting the values. Now, one more time, 135 sits right here. So that's a 45. And I know the tangent values at all the 45s. Tangent at 45s, tangent is 1 here and 1 here. At the 45s, a negative 1 here, negative 1 here. I do know tangent 135 is simply negative 1. Plus tangent 60 is root 3. And again, I just have that in my mind. 60 degrees is this one. The coordinates at 60 degree or cosine is half. This one's root 3 over 2. And when we do y over x, we get root 3 over 1 minus, well, I don't have to recompute them again because I already just did. Tangent 135 is negative 1, so plug that in very carefully in parentheses, times root 3. And clearly you can see from here, it has turned into a computation problem. Can we handle radicals, fractions, yada, yada, yada. Excuse me. Very carefully, numerator can be written as that. Not that I had to, but I just rearranged them. On the denominator, I'll have 1 plus root 3, because 2 negatives will make a positive, and then that's what I have. I mean, yeah, I kind of simplified it as much as I could. Can't cancel them. Please don't be thinking that these two can be canceled. No, 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 no. In the numerator, if you have 5 minus 1 over 1 plus 5, you would never cancel these out, because canceling this out leads to negative 1. But if you don't cancel them, which is the right way, that's a 4, and the denominator will be a 6, which is 2/3. Totally different answers. We know this is not the correct route, so none of that can be canceled. We can accept that as an answer, except there's a radical in the denominator. Now, this is a slightly different type of radical. I'm just going to rewrite it here. Previously, when we ended up with this kind of stuff, y'all are experts at rationalizing now. Times it by root 3, times it by root 3. And then root 3 times root 3 is 9, which is back to 3, and then you stick them together. This is what we used to do. But now we do not have just a root 3 sitting there. It's 1 plus root 3. So it's like 1 plus root 3. So if I multiply by root 3, that's not going to work. You have to tackle this as one term. So the best way to take care of this is you could multiply by the exact same thing, but I know that that's not going to get rid of the radical. Why? Because 1 plus root 3 times 1 plus root 3 will actually lead to this. If you FOIL it, that's 1 plus root 3 plus root 3, so plus 2 root 3, and then this times this will be a 3. So that turns into 4 plus 2 root 3. So if you notice, I still have the radical in the denominator. So multiplying by the exact same polynomial is not going to help. When this happens, we multiply the denominator by its conjugate. That's the best way to get rid of the radical. And we did that last time in the class. Because when we multiply by the conjugate, we now have a plus b times a minus b. That leads to a squared minus b squared. What's my a here? 1. 1 squared. And the minus b is this. So that's squared. And that just cancels the square root. Because when you square, square root is gone. 1 minus 3, which leads to negative 2. And that takes care of the radical in the denominator. So, bottom line, I mean, I pretty much had the answer except this whole rationalizing deal here. So we're going to multiply by its conjugate, and hence I have to do the same thing to the numerator. So in the numerator, I have root 3 minus 1 times 1 minus root 3 over, like I said, this is your a plus b, a minus b, and hence that can be combined as a squared minus b squared, and that's what I'm going to do now. 1 squared is 1. minus b squared is root 3 squared, which is simply 3. So I'm going to erase that, and there's 3 there. Sweet. If you go ahead and FOIL this real quickly, you'll get root 3 and then times minus 3. And then here, that gives me negative 1. And here to here is plus root 3 over negative 2. And you can stick the negative on the outside here. There's no need to put the negative in the denominator. In the numerator, of course, there's a negative here. We have 2 root 3 minus 4 over 2. There's still a negative sitting on the outside. I'm just getting tempted to pull out a 2 because I know that will cancel with the denominator. 2, and now you see that 2 can be canceled. So we have negative of root 3 minus 2. I mean, it can be written as negative root 3 plus 2 as well. Same thing. Oh boy, the computation part was much longer than the trigonometry itself. And we have simplified it as much as we could. That's the exact value. No decimals allowed. Now I know we're done. I mean, there was a lot of talking involved just because this was the first example, so I was trying to explain how multiplying by conjugate is going to help you get rid of the radical. Hopefully in the next examples, we will be able to get to that ourselves without having to explain all of it. All right. So those are two examples that are only degree kind of problems. They're only degrees. I've got to show you what if we have a radian going on. Trying to flip through these to find them. I want to make sure that I've taken care of all the negatives carefully. 2 root 3 minus 4. That part is correct. Yeah, that part is also root 3 plus 4. I just want to make sure when I undistributed it. Yeah, it looks right to me. Because that's the 2 positive, and then this will give me a negative, which is what it was. Yeah, that does look right to me. If there are any errors, we catch it and let me know. All right, third example. We were not in degrees, but we are in radians. Fun, fun. This one says find exact value without calculator for sine of pi over 12. Sine of pi over 12. That's all I have to find. But we do know that our unit circle and our special right triangles do not go up in 12ths. Having realized that, I have to break this up. Just like in the other examples, you have to break it up into two special triangle deal. But with radians, it can be a little kind of deal, right? There are two options here. Like this is, so the 12th can be broken down. Let's write down all the ways we can break down 12. 1 and 11, right? So basically pi over 12 and 11 pi over 12. But I need to be able to get 1 pi over 12. So that's not going to work. I need to be able to subtract it. So 7, like here, 4 pi over 12, and then minus 3 pi over 12. Like this will give us pi over 12. Those are the first two numbers that came to my mind. Others can be 7 pi over 12. I mean, there could be so many combinations. But the idea is, can we handle these two? Are these two our special right triangles, yes or no? Like, for example, this is nothing but pi over 2. And then 7 pi over 12 is not a special triangle. So this split doesn't work. 8 and 6, and 8 and 7, well, 7 pi over 12 doesn't work. So don't be using anything that has 7 pi over 12. 9 pi over 12 minus 8 pi over 12. Well, 9 pi over 12 simplifies to 3 pi over 4. Oh, that's, we go up in the fourths on the unit circle, so that works. And then minus, this one is 3 pi over, not 3, this is 2 pi over 3. 2 pi over 3. Yeah, that also is on unit circle. 2 pi over 3 is also in unit circle. And then if I look at the first one that I did, this one, 4 pi over 12 simplifies to pi over 3, and then 3 pi over 4 simplifies to pi over 4. Oh yeah, both of these are also in unit circle. So I actually found two pairs. It depends on whichever you want to use. Sine pi over 12 can be rewritten as sine of, if I pick the very first one, 4 pi, no, I'm not going to write 4 pi over 12. It simplifies to pi over 3, and then minus pi over 4. Now, I haven't really changed the question. I have rewritten pi over 12 as a subtraction problem. I also want to give you this other option of degrees. Like pi over 12, if you were to convert pi over 12 into degrees, it's actually 15 degrees. And now this one, you might be able to split quicker in your mind that, hey, I can write this as 45 minus 30 degrees. Well, then I'm like, oh, you could do pi over 4 minus pi over 6. That's an option. And this quickly jumps into giving you the split. That's just another option, basically. So if you notice, we've come up with this, and even the last one here would have worked. And every student is going to do differently as long as the subtraction leads to pi over 12. That's the idea. Like when I subtract these two, does that give me pi over 12? That's the idea. And it does. I just double checked it again. Let me check this one. This will be 4 pi minus 3 pi over 12, which will be pi over 12. Yeah, that one works as well. And then there was one here that I used, this one. So 3 pi over 4 minus 2 pi over 3. The idea is, does that equal pi over 12? 9 pi minus 8 pi over 12. Yep, it does give pi over 12. So all three were possibilities. Two possibilities were direct handling radians, and one possibility was converting it to degrees and getting it. So I'll leave it up to you of how you want to split it up. The idea is still the same, being able to use our special right triangles. Okay, and then this is the a minus b type. So I have sine a minus b, and the formula for that is this one, sine a cosine b minus cosine a sine b. So this will spread into sine of pi over 3 times cosine of pi over 4 minus cosine of pi over 3 times sine of pi over 4, and I know all of these values. Okay, you can again be creating triangles unless otherwise if you know, then it's much easier. Like sine of 60 degrees is sine of 60 is root 3 over 2, and then times cosine of 45 degrees is root 2 over 2 minus cosine of 60 is half, and then this one is back to root 2 over 2. Okay, I can already see that this problem is not going to have any radicals in the denominator, so this one's going to be a quicker problem. Over 4 minus root 2 over 4. And the best I can do is combine them because they have the same denominator, and I have found the exact value of sine pi over 12. This was not that big of a problem. The idea was how to break pi over 12 to get into special right triangles. Let's show one more. Let's see if we can do this one. Another one handling pi, basically. So I have cosine 7 pi over 12, and they're saying find exact value. Well, you're going to do the same thing. You're like, well, I don't know the 12th on the unit circle, so somehow I have to break it down, either into an addition problem or subtraction problem. That doesn't matter. Break it down into something minus something or something plus something. So 7, to get 7 pi over 12, try different times. 4 and 3, 4 pi over 12 plus 3 pi over 12. This simplify, we just did it actually, pi over 3, and then this simplifies to pi over 4. Oh, this works too. The very first one works. The other thing is you can, like I said, if you want to, excuse me, you can convert this to degrees first. Pi over 12 is 15 degrees, and times it by 7 makes it 35. So that's 105 degrees. If you would rather split 105 degrees, well, start with 30, like I said. 30, that makes it 85. No, 75. So that's special right triangle, but that's not. And move on to 45. Subtract 105 for 45, 60 degrees. Oh, there we go. So 45 and 60, because, yeah, those are both special triangles. This converts to pi over 4, and this converts to pi over 3. And then you got the same thing that I got without degree conversion. So I'll leave it up to you. Pi over 4 plus pi over 3 is what I have chosen to split it into. From here, it turns into cosine AB formula. So that's your A, and that's your B, and cosine A plus B. Cosine A plus B is cosine AB minus sine AB. That equals cosine A times cosine B minus sine A times sine B. Okay, cosine pi over 4 is root 2 over 2. Cosine of 60 is half. That's again root 2 over 2. And sine of 60 is root 3 over 2. Very similar question. So root 2 over 4. Remember, this is multiplication, so you have to actually multiply the denominators. Minus root 6 over 4. And the best you can do is combine it. Root 2, root 6. The cosine 7 pi over 12's exact value is root 2 minus root 6 over 4. Now, these are forward-going type of problems. Like, we're breaking it apart and using the formula and then finding the answer. The other way around to this is if they already give me a broken apart situation and they're asking me to find the value of it. For example, this one says find exact value of sine 80 degrees times cosine 20 degrees minus cosine of 80 degrees and sine of 20 degrees. Find exact value of this. Well, clearly this one doesn't need to be broken down, but we got to be able to identify that if you notice, if this angle is called A and this angle is B, then we are repeating those same angles, AB, and this looks like sine A cosine B minus cosine A sine B kind of formula. I'm like, wait a second, that could be a difference formula. So let's go check. But sine times cosine is sine times cosine times sine. Sine times cosine, sine times cosine, and minus cosine of the first angle, sine of the second angle. That looks like sine A minus B formula. Sine A minus B formula. And please verify it's in the same order. Sine of the first angle times cosine of the second angle minus cosine of the first angle times sine of the second angle. And that's what this is. Sine of the first, cosine of second minus j. So like, that's the, oops, cosine. That's the sine difference formula. Okay. So this must be sine, the difference of the two angles. Okay. Which means this can be combined as sine of 80 minus sine of 20, because that's the A and that's the B. And then from here, actually I should delete this because I kind of lost the flow here. Flow isn't very nice. not even here. So keep going this way. So sine of A minus B. Now clearly that combines into sine of 60 degrees, which we know is root 3 over 2. So the exact value of all of this is root 3 over 2. And not too long, it was mostly about identifying what's going on here. I'll show you a similar one in radians. So example 6, find the exact value without using calculator of this times sine of pi over 12. Like, this is obviously not the breaking down type. Looks like it's already broken down for me. So I'm like, this is cosine of an angle times cosine of a different angle plus sine. Okay, I can't call this A. If you notice, A is pi over 12. So it looks like this is sine of B times sine of A. Order doesn't matter with multiplication. You can put any of those. I'm like, so cosine AB plus sine AB. Let's go find which formula is that. Cosine AB plus sine AB. There you go. Cosine AB plus sine AB. It's cosine of A minus B. Cosine of A minus B. Cosine of A minus B. Hence, this must equal, I can compress it to cosine of A minus B. Honestly, I could have switched the order of these two so that the bigger angle was ahead. Now that boils down to cosine of negative 4 pi over 12, which simplifies to cosine of negative pi over 3. Yeah, and then cosine of pi over 3 is half. So cosine of negative pi over 3 would also be half, actually. Yeah, half. Again, I was doing this from the unit circle configuration, but if you were to draw triangles, negative pi over 3 is here. It's a negative 60 degree, basically. So this must be negative root 3. This must be 1. This must be 2. And the cosine there is adjacent over hypotenuse 1/2. All that simplifies to 1/2. Okay, and the last one for the video. This one's interesting too. This one says find exact value of secant of negative pi over 12. Interesting. Secant of negative pi over 12. You could convert it to cosine, but please don't be thinking that because I converted it to the reciprocal, you can reciprocal the angle. The angles don't work that way. So this would be incorrect way of doing it. If it was a value, I could have reciprocaled it. That's an angle. We're not going to reciprocal the angle. So what we're going to do is we're going to first find cosine of negative pi over 12, find that answer, and then we will reciprocal that answer. Because whatever cosine at that angle is, secant at the same angle has to be the reciprocal of that. Then comes in the same deal, how do I break it up? Negative pi over 12 is negative 15 degrees, if you want to convert it to degrees. And now 15 degrees can be written as 60 minus 45, or negative 60, and then positive 45. That's one combination. Negative 45 and positive 30 would also work for that. And honestly, any of this pair will work because these are special triangles, these are special triangles. It's just your pick. The answer is going to be the same. So I'm going to pick the bottom one. I'm like, okay, I'm going to split this up into, oh, by the way, convert that, then negative pi over 4, and then this would be pi over 6. So I'm like, negative pi over 4, and then plus pi over 6. It's actually best to write it backwards to use the subtraction formula instead. There, right? It has turned into a subtraction cosine problem. So that's my a minus b of cosine. Let's go get that formula. Cosine AB plus sine AB. Plus sine A times sine B. Okay, just follow along. It's not going to be negative pi over 4. It's just cosine of B, not cosine of negative B. We have already taken care of the negative by using the negative formula. Cosine of 30 degrees is root 3 over 2. Cosine of 45 is this. Sine of 30 is half. And sine of pi over 4. So that's root 6 over 4 plus root 2 over 4 plus root 2 over 4. Okay, so the answer thankfully does not have a radical in the denominator. So this should be it. Yep, which means basically, oh no, no, no. Remember the question was originally a secant question? So this is the value of cosine of negative pi over 12. See, I was almost about to drop that myself. I'm like, oh no, 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 no. We have to find secant at that same angle, which means what I have here, I have to flip it. That's the secant value. And flipping has created the issue where I need to be able to get rid of the radicals in the denominator. Remember those kind of radicals I showed you in the very beginning? You got to multiply by its conjugate. That's the only way to get rid of them. This turns into a plus b times a minus b, which should be compressed into a squared minus b squared. So a squared minus b squared. In the numerator, I have 4 times root 6 minus root 2. In the denominator, we have 6 minus 2, which is 4. And look, the 4 is cancelled. So this simplifies to root 6 minus root 2. Secant negative pi over 12. Oops, that disappeared. You want to be able to see the radical sign. There we go. Now we have done it. Well, quite a lot of work. But that was it for now. I'm pretty sure the video's gotten pretty long. See you in the next video. There's more sum and difference, identities, and proofs coming.